Thanks for coming along. I am Ben Healey and this talk will be about using the Python-based natural language toolkit to automate document classification. My background is in market research and analytics, so my day job primarily involves coding in SAS, working with databases and Excel to extract business insights. I also advise on survey design and development. I am relatively new to Python and have recently had reason to use the natural language toolkit to help me with some document classification I need to do. So, when the Kiwi PyCon call for papers came around, I thought this would be a good opportunity to learn some more about this process and share my experience with others. My aim today is to cover the overall process involved in developing a document classification algorithm using the NLTK. You'll come away with an understanding of where to start if you want to do something similar yourself. I'll also introduce some terms specific to machine learning and the NLTK. In particular, I'll cover the need for automated classification, reasons to use natural language toolkit, and the alternatives available, machine learning tools in the NLTK, and the naive Bayes classifier in particular. Using Python for data preparation, training and assessing your classifier, tricks and traps, and, finally, further resources to explore. The need for automated approaches to common document classification tasks is self-evident. Individuals and businesses are dealing with an increasing volume of information in a variety of formats, be it text, audio, image or video. You may think of web-based content generators and social media as being key contributors to this deluge, but organizations are also collecting more complex data internally from customers, employees and other stakeholders that they need to make sense of. Unfortunately, people don't scale. We are comparatively expensive and get tired or bored easily. We are also quite subjective and vary from day to day in the way we apply classifications. So there are potential financial, consistency and time gains to be made from automating repetitive document classification tasks. Some common applications include spam filtering, document language identification, for subsequent translation. For instance, Google Translate uses this to automatically detect the language of a text snippet you want to translate into English. Sentiment analysis. For instance, an organization may analyze the tweets about its new product to track whether or not the comments are generally positive, negative, or neutral over time. Google AdSense and other contextual banner ad networks, which choose the banner ads to place on a web page by first classifying the topic of the text on that page. One application that is not common, but which we'll examine today, is document classification to aid the legal discovery process. I managed to find one organization called Blackstone Discovery that is doing this sort of thing commercially. So, while the example I'll use today is contrived, it does reflect a real-world problem. Before getting into the example, it is worth considering the process and tools we'll be using along the way. I've chosen the Natural Language Toolkit for this talk, but there are a range of other tools that can be used with Python to build automatic classifiers. Examples include Scikits, which has a number of machine learning modules in its Learn package. Orange, which is a data visualization and analysis toolkit written in Python. It even has a visual programming interface. And the ever-popular R language, which can be accessed via a Python interface called RPy. For a good discussion of these alternatives and others, do a search on Stack Overflow for the phrase machine learning using Python. The reason I've chosen the Natural Language Toolkit for this talk is that it has a particular focus on document analysis. As such, it contains some very useful tools for manipulating text that don't come as standard in some of the other Python-based alternatives. Since it also contains a number of fairly standard machine learning classifiers, it is a great tool to get started with automated document classification. This diagram outlines the process for building an automatic classifier using supervised machine learning. The bottom line presents the end goal, which is to be able to take a document that we do not have a classification for, extract some features from that document, and run those features through our train classifier, so that we can get a predicted and accurate classification for the document. In order to achieve this, the classifier has to be developed, trained, using a set of documents for which the classification is known. Ideally, the development set will contain a large number of documents that are representative of the kind of documents you'll want to classify automatically. For each document in the development set, you'll need to extract a range of features to feed into the classifier during the training stage. Features could include things like the number of words in the document, whether or not a specific word, anagram, or group of words, ngram, appears in the document, who the sender of the document was, the percentage of the document written in all caps, and so on. Different machine learning algorithms can be used, and some are more appropriate for document classification tasks than others. But we'll talk about that some more later. At this stage, the key things to take away from the diagram are that the quality of your development set, your choice of features to extract, and the machine learning algorithm you select will all have an impact on the reliability of your trained classifier. The modules listed here come bundled with the NLTK. They can be used in the feature extraction and machine learning phases of the document classification process. These are just a sampling of what is available, so you should have a look through the NLTK documentation to identify other components that could fit your use case. Looking first at feature extraction. The corpus module contains words and stop words. Words is a list of English words, which can be useful if you want to check whether your documents contain a high proportion of common English words. You might do this if you are building a classifier to tell if the document is English or not. You could also use it to help detect if a document contained high levels of jargon terms. Stop words is a list of high-frequency words such as the, to, and also that you often want to filter out of the set of words in a document that make it through to the feature list. The STEM module contains tools for normalizing the words in document to their common root. For instance, the words programmer, programs, programming and program would all be stemmed to program by the Lancaster stemmer. Stemmers are useful because they help your classification algorithm use the root of the word as a signal to pick up on, rather than using different variants of the word as different signals. The Tokenize module provides tools to split your text down from a collection of words and symbols into discrete units. For instance, the word punk tokenizer breaks a text into words or subwords based on the presence of punctuation and white space. Tokenizing is the common way to get a list of anagrams from your document that can then be included as features to be passed to your classifier for training. You can try out different stemmers, tokenizers and other NLTK tools on the StreamHacker blog by Jacob Perkins. See http://streamhacker.com or http://textprocessing.com/demo/. NLTK also contains tools for finding and selecting collocations on words that commonly appear together. For instance, the bigram tools help identify and select two-word combinations that appear throughout a text. There is also a set related to trigrams, three-word combinations. The presence, or not, of these word combinations can also be included as features to be passed into your classifier for training. Turning to machine learning algorithms, the Natural Language Toolkit contains a handful of commonly used classifiers including a naive Bayesian classifier, a decision tree classifier and a multinomial logit classifier, called Maxent. It also provides an interface to the Java-based Weka collection of open-source machine learning algorithms from the University of Waikato. It is beyond the scope of this talk, and my knowledge, to go into the details of each classifier. However, each classifier has its own profile of computational requirements, flexibility and interpretability. So, It is worth investigating the most appropriate classifier for your purpose and also testing different classifiers to see which produce the best outcomes for your datasets. In addition to the classification algorithms themselves, NLTK provides some tools for assessing the performance of your train classifier under the classify.utils module. The accuracy test is just one of these, and we'll look at some alternative ways to assess your classifier when we run through the example. I used a naive Bayesian classifier for today's example. In essence, this classifier generates an estimate of the likelihood that a document is of the class of interest, or label, in the above formulae, by looking at the features that it has and computing the likelihood that a document with those features would be of the class of interest. The likelihood for each feature and label is determined during the training phase, by iterating through the development set of documents for which both the features and label are known. Thus, the classifier extrapolates the probabilities it establishes during training to new documents it encounters. The classifier is Bayesian because it employs Bayes' theorem to build up conditional probability distributions for the labels and features. It is considered naive because it assumes that the occurrence of one feature is unrelated to the occurrence of another feature. That is, it assumes the features are independent. This assumption is frequently incorrect. Nevertheless, Bayesian classifiers have proven to perform well despite this apparent flaw in logic. Those interested in learning more about the mathematics underlying the classifier should head over the related Wikipedia entries for naive Bayesian classifier and Bayesian spam filtering, which contain some worked examples. Now that we have covered the process and components necessary to build a document classifier using the NLTK, I'd like to jump into an example. For those of you who haven't heard about Enron, it was a very large energy and commodities trading company which went spectacularly bankrupt in late 2001. The ripples of its bankruptcy were felt throughout the American financial and political system. Subsequent investigations surrounding its accounting practices led to the arrest and imprisonment of a number of its key executives, along with the downfall of one of the world's largest accounting firms, Arthur Andersen. As part of the investigations that went on, Enron was required to provide prosecutors with the organization's emails for a period prior to the collapse. Those emails subsequently made it into the public domain, and I thought they'd be an interesting set of documents to build some classifiers on for this talk. In total, just over 500,000 emails were released as part of the Enron document discovery process. That's a lot of documents to try and look through if you are a prosecutor attempting to identify key documents for your case. It is likely to be prohibitively expensive to hire a group of people, even interns, to look through all of the documents. It would probably also be very difficult to build a classifier to try and pick out key documents since, by definition, these are rare. If you think about these key documents as needles in a haystack, you would spend an inordinate amount of time trying to find examples to feed into your development set. By the time you'd found them, you would have probably looked through half of the emails already. Of course, if you had some keywords you knew would exist in the documents, or you knew who the key players were in the case, you could search for key terms or only read the emails from certain individuals. But if these avenues were exhausted, another approach you could take is to try and reduce the size of the haystack. Specifically, if you could identify the types of documents that are very unlikely to contain information you are interested in, and then have a classifier run over the entire set to identify documents that are likely to be of those types, you could reduce your workload significantly. This would allow you to focus your efforts on documents that weren't clearly hay. Although the full set of 517,000 messages was available as an archive, it had not had much in the way of elementary data cleaning done to it. So, instead I have used a subset of just over 20,000 messages that have already gone through some cleaning. There is a link to the download at the end of the talk for those interested. One point to note is that the subset comes from 7 Enron employees who had a particularly large number of emails in their folders. So, the subset is not likely to be representative of the entire message set owned. As a result, Any classifiers built on them could not be expected to perform well over the entire set. The messages came as separate plaintext files within a folder structure reflecting the owner and email subfolder the message was assigned by the owner. Although I have not used these elements of structure as features in developing the classifiers here, this sort of information would be relevant to the classification task and might be included in a more comprehensive modeling project. I used the miscalloc interface for Python, along with functions from the standard OS and string Python modules, to import each plaintext file, separate out some key fields such as the sender, recipients, subject line, and message body, and finally insert a row into a dedicated miscal table. As part of the extraction process, I also allocated a random number to each message and created some derived fields such as the number of people the message was sent to, the number of words in the body, and the percentage of words that were in all caps. The random number was used to select a subsample from the full table to use as a development set, while the derived fields were created as features to be fed into the Bayesian classifier. As an aside, I've found that it is generally a good idea to allocate a random number to each record when you are creating a dataset. Most databases, be they relational or NoSQL, don't handle random selection tasks very well, so it can save time to have a way of randomly ordering records pre-baked into your data. Those interested in the details can download the code at benhealey.info. Just do a search for Kiwi PyCon to find the files. It is worth noting that more cleaning could have been done to the messages. For instance, a number of the messages are forwarded or replies. So, they contain two or more messages in one, along with the original message metadata. This sort of duplication and noise might confuse a learning algorithm. Alternatively, they may also help the algorithm pick up on key signals about the message context. Whatever the case, an attempt would ideally be made to train the classifier with and without the presence of these confounds to determine the effect on model accuracy. Here is one of the messages from the set. I classified this as a legal/regulatory message, but it is possible that someone else might classify it as an administrative message since it pertains to a meeting agenda. The key point is that any ambiguity inherent in the message context will likely flow through into ambiguity in the training phase and degrades the performance of the classifier. This message is a little more clear-cut. I've classified it as an IT message, since it pertains to the output from an automated process. At a glance we can see that messages such as this are likely to contain signals that should be easily picked up by a classifier. For instance, the message is short, contains a number of all caps words, and is likely to contain symbols such as and GT semicolon and GT, that would not normally appear in human messages. Look at the message a few seconds more and you will probably come up with a handful of other signals that might help a classifier distinguish this sort of message from another. This is a key way to come up with features to feed into your classifier. So, having a human parse some of the documents is a key part of the idea generation and model training phase. Another aspect that may require human involvement is in assigning a class to the development set. For this example, I went through and tagged a random sample of 1000 messages with one or more classes. Don't try this at home. It is quite boring. The more sensible approach, if feasible, would be to outsource the tagging to a crowdsourcing service such as Amazon Mechanical Turk or Crowdflower. I did actually attempt to put my sample through Crowdflower, but came up against a number of formatting issues with the messages. These, and the looming conference deadline, led me to decide to tag them myself using a hastily created mSuccess form instead. If you are particularly lucky, you may have a development set that is already tagged, or that it is trivial to tag automatically. For instance, if you were building a classifier to predict which stocks would rise in value in future, you would be able to tag an historic training set very easily using historic stock price information. A couple of points to note from this chart are, my intent here is to build one classifier per class. For instance, I'll build one classifier that predicts whether a given message is related to external relations, or not. Another classifier will predict whether a given message is related to infotech or not, and so on. Just be aware that there are classifiers that will allow you to predict across multiple classes. Indeed, you could even combine the results from the separate models in this example to get one overall predicted class for each message. However, this is beyond the scope of this talk and my knowledge at this point. You'll notice that the external relations and social/personal classes doesn't have many messages in them. This is likely to hinder development of an accurate classifier for those classes, since the classifier will not have many examples to train on. In contrast, there is a better chance we will be able to build an accurate classifier for the IT, regulatory, and deals classes with the development set of 1000 randomly selected messages in place. The next step is to pull out a range of features for the classifier to train on. I've taken a kitchen sink, one-size-fits-all approach for the models in this talk, but with more time I'd select features for each model in an iterative process. For instance, you'd throw in a bunch of features into the first model, say, for it, check out its accuracy, then whittle down or modify the features and see what effect that has on accuracy. What you are aiming for is a model that is both robust, that is it gives good predictions against a test set of messages, and parsimonious, that is it uses the least number of features necessary to achieve its accuracy. Simply throwing the kitchen sink at your model, as I have done here, increases the chance of overfitting, which is where the model performs well on a training set but poorly when you attempt to apply it to documents that it was not trained on. This slide lists the core NLTK modules I used to expand out the feature set for my models. You can download the code relating to this at benhealey.info. A couple of points worth noting about the feature development stage is that you'll generally be aiming to generate features from your documents that are either Boolean or nominal, also known as categorical. By nominal I mean a short list of possible categories, not necessarily with any inherent order. The example on this slide shows a set of categories for the num_words_in_body feature which do have an inherent order. Long messages are larger than medium messages, but a Bayesian classifier is ignorant of this. As far as it is concerned, you might as well be giving it a list of colors. All it cares about is that you are giving it a feature which casts a message into a specific, mutually exclusive group based on this thing you've called num_words_in_body. A Boolean feature is formatted as its name suggests. The token-based features, grams, bigrams etc. extracted using some of the NLTK tools are generally presented in Boolean format to classifiers for training. Either the feature exists for the document, or it doesn't. Note that you could also feed numeric features into the classifier. However, you need to take care to avoid a situation where the feature can take on so many different values that there are not enough instances of each value in the development set for the classifier to build up good history of that instance's co-occurrence with each document class. This is why I created the num_words_in_body feature as a series of bins rather than leaving it as a discrete numeric variable. One final thing to note is that all of the features I've extracted are ones that I will be able to extract for any new, unclassified, documents I want to feed into the classifier. If they weren't, I couldn't expect any resulting trained classifier to accurately predict the class for new documents. Much of the grunt work has now been done. The data is in a reasonable state for modeling, a range of features have been extracted, and the development set has at least one class assigned to each document. The next step is to train a classifier using the data and assess its accuracy. NLTK makes this relatively simple. As the slide shows, the development set is split into two chunks at random. The first chunk, the training set, is used to train the classifier. The second chunk, the test set, is used to test the model's accuracy. This second chunk is sometimes also referred to as a holdout sample, and acts as a tool for determining how the classifier might perform in practice if we were to ask it to predict the classes for documents that it had not seen during its training. You can test a model more rigorously than shown in this slide, by performing multiple rounds of cross-validation. But this is enough to provide a good overview of the process. You'll see here that I have used two of NLTK tools for assessing accuracy, the accuracy module and the show_most_informative_features method of the classifier itself. Again, I've used these for illustrative purposes, but there are other testing metrics that could also be applied to assess the accuracy of the model. Again, you can get my code for this from benhealey.info. Here are those two performance metrics for the IT classifier. The accuracy figure of 0.93 indicates that the classifier allocated the correct class, it or not it, to 93 of the test cases. This is a promising sign, and not unexpected given the general structure of these types of messages. The most informative features list outlines the features that are most useful to the model in helping it distinguish messages from other messages, along with the likelihood ratios for those features. It shows, for instance, that messages containing the word, or token, txt are IT-related about 150 times more often than they are non-IT-related. The features listed make sense given the IT context, so we can gain some confidence that the model is working okay. This slide shows the same metrics for a classifier built to distinguish deal or trading messages from other messages. Again, the results are generally promising. Accuracy is not as good as for the IT model, but it is still reasonable, and the most informative features make sense. The terms nom and nomin are common trading terms, while mtu and xu relate to volume units. The likelihood ratios are not as high as some of those identified for the IT model, so this model may have more difficulty distinguishing between deal and non-deal message types, and here are the metrics for a poorly performing model. Social/personal. The accuracy figure of 0.48 suggests this classifier is having quite a bit of difficulty distinguishing social messages from others. If you cast your mind back to the chart I presented earlier, you'll remember that very few messages were tagged as social in the training set, so the classifier didn't have much to go on. Given that, this result is not surprising. More work would need to be done to get more training cases for this class, or to tease out some more features that might give the classifier a better chance of predicting correctly. One positive is that the informative features seem to make sense given the context. Most of the terms are those you would expect to see more often in personal or social messages, and less often in other types of messages. Although the accuracy metric presented earlier can be a good indicator of classifier performance, it is dependent on the rate of incidence of a class in the test set. For example, imagine a classifier for the class hens. Looking at the charts for the deal classifier, it appears that this is also performing well, although perhaps not as well as the IT classifier. The table suggests that the classifier is having some difficulty distinguishing deal messages from other and legal messages, so some more work could be done to tease out features that might help it there. Finally, the social classifier is performing about as badly as we might have expected from early indications. The table suggests that the model is having difficulty distinguishing social messages from other messages across most types. This is reinforced by the information in the chart, which has the model performing only slightly better than what we might expect by chance. At this point, if we cast our focus back to the prosecutor in the Enron case, we can start to see a way forward with automated document classification. Even after this beta run-through, the prosecutor could be confident that a classifier would help them eliminate messages, estimated to be around 17 of all messages in the sample, from the haystack. Similarly, if some deal messages were likely to contain information of interest to the case, there is now a classifier that can be used to identify those messages from the haystack that should be prioritized for human review. And, as those messages were reviewed, more information would become available that could then be used to feed into further development of the classifiers. So there you have it. We've covered the process for developing automated document classifiers using the NLTK and Python, with the Enron emails being an illustrative example. Hopefully you'll be able to see how this sort of modeling could be useful to you professionally or personally. I've mentioned a few gotchas along the way, but it is worth reiterating them before I finish up, since they can have a big impact on the success of your classifiers. Try to avoid using a biased sample to train your classifiers. If your development set doesn't contain the same general mix of documents as those you expect to apply your classifier to, you can't really expect your classifier to perform well in practice. Be careful of the accuracy metric, particularly if you are building a classifier for a rare document type. There are methods for dealing with modeling situations for rare events which I've not covered here, and it pays to take a look at a few different performance metrics for your model before you finalize and rely on it. Your prior knowledge, or that of subject matter experts, can be very useful for identifying key features to give your classifier for training. Ultimately, you are trying to get the classifier to pick up on knowledge that you probably already have as a human, so that you can apply that knowledge at scale. So, you need to think about what it is that enables you as a human to distinguish one document type from another and formalize that as much as possible so that it can be used in an algorithm. Don't expect the first classifier you build to be the best one. Like most things in life, there is a learning cycle involved here. You'll probably go through a number of draft classifiers before you settle on a final classifier that is reliable and parsimonious. Even then, once the classifier is in production, it will need to be tweaked as new knowledge about the domain becomes available. Those interested in trying their hand at automated classification will find the following resources useful. The first link is to the NLTK website. There, you'll also find a link to a book covering the Toolkit, natural language processing, and document classification. The second link is to a downloadable archive of the Enron emails. Those interested in learning more about machine learning should also consider taking the free online course being offered through Stanford in October to November 2011. You can sign up at mlclass.com. Finally, Jacob Perkins runs a blog about Python, natural language processing and machine learning, which contains a number of very useful examples, demos, and articles.